Good afternoon, dear guests, dear teachers, and dear students, and dear everybody who is here, coming for this special event scheduled for afternoon. Today afternoon we have 2 lectures prepared for you, and there is no need to introduce the titles, because that's the reason why you are here. I guess that you all know why you are here. So let me at least say a few words about the first speaker, Alejandra Magana. She is from Purdue University, as well as the next speaker, Bedřich Beneš. So to say something nice about Alejandra, the nice thing is that she is a teacher at Purdue University. She teaches future engineer students from the area of technology, computer science, and things like that. And at the same time, she is a researcher in pedagogy in the area of education. And she is able to combine the real teaching experience with research how to teach in new ways. And I am really happy that she will share her experience this afternoon. Just a small comment about the history of Alejandra. Alejandra studied in Mexico at the prestigious Institute of Tecnológico de Monterrey. Then she moved to Purdue, having a master and PhD degree from Purdue, and currently she's full professor at the Purdue University, Indiana, USA. So Alejandra, welcome here at Czech Technical University. And please share your experience about the topics that is shown up.
Perfect. Oh, I have my own mic.
This is my phone.
Yeah, that's yours.
Mic, and also this is mic for you for the discussion, which will be hopefully fruitful and long. We will see.
Okay. Good afternoon, everybody. I think it's still the volume is still quite high, so I'm putting this mic a little bit away from my mouth. I like to speak loudly, so I don't want to damage your ear. So, okay, it's my pleasure and honor to be here today. I'm going to tell you about what we have learned in the last 15, 16 years of doing research in the context of classrooms. And I'm going to tell you about this particular type of learning, which many people call computational thinking. There are many ways in which researchers have this defined computational thinking. I guess the topic of computation, modeling, and simulation falls within that definition. Many of the things that I will say today might be familiar to you if you are a student learning computing in computing domains. Maybe as an instructor as well. But I think the side effect of doing this is that we need to do the research in the classroom. We need to document that. So again, many things will be obvious, but in some ways, the research might be lacking. It's more our intuition and our experiences. So this is the motivation for my talk today. Many of us see students experiencing sometimes anxiety or frustration as they learn. Maybe that is not the case. Maybe even ourselves at some point as we were students had a similar experience, maybe not. But something that we know from research is that, again, I'm going to say computational thinking. I'm going to come to a definition, but in general, computational thinking is a complex form of learning. It takes some time to develop the skill, and is not as intuitive as as other type of domains. Students may have low self-efficacy beliefs, meaning that their confidence might be low, meaning that some students, if they are computer scientists, of course they value it, but in many other disciplines that use computing, like engineering, students may be computing averse. Basically, they don't want to engage in programming, even though they are pursuing engineering degrees. So we know that the students sometimes think they are not good at it. It is documented in the literature that women, in particular, they have lower self-confidence than male students. So part of the problem is that it's an abstract form of learning, but at the same time, when you apply it to solve science or engineering problems or innovate in science and engineering, you may need to apply multiple type of knowledge. You need to learn mathematics, programming, and of course the science itself, you know, the engineering principles and so on. So there are many things happening at the same time when students learn about computation, modeling, and simulation, which for now I am using computational thinking. So what can we do to help our students move from a situation like that to a situation like this, where they are more confident and, you know, in a way they could enjoy potentially learning about these abstract topics? I see few smiles. So let me give you an overview of my presentation. I will first give you a quick overview of my research program. This is one part of it, but I do study other things in the context of learning. I guess an important distinction between the Faculty of Education and Pedagogy, they mainly focus in education in general, but my expertise in engineering and computing education, so the disciplinary background is very critical as well. So without my training in engineering, I probably wouldn't be able to do this type of research, because you need to combine methods in education in the context of the discipline. So I will give you a big perspective of that. I will walk you through 3 studies in a way. One, the first study will allow us to document what is the problem. The second one will help us connect it with the literature. And the third one will focus more on what are the kinds of solutions that we can provide once we have identified the problem. And then, you know, I will, you know, summarize my findings and discuss concluding remarks. So my research program is looking at computational thinking in the context of science, technology, engineering, and mathematics. That's a very common term in the US, STEM disciplines, so all biochemistry, physics, and then engineering could be biomedical, mechanical, electrical, and whatnot. So it's not computer science, it's computing in the context of a science or an engineering discipline. So there are multiple definitions of computational thinking. Some of them involve focusing on data science, others using programming to solve problems, modeling and simulation. Also, systems thinking is part of that. And then at the top, how to learn about, I guess, artificial intelligence as well in the context of programming, so learning the algorithms and whatnot. So my talk today will be situated in this space. I will look at modeling and simulation primarily, but we will have a close eye into programming practices. But the findings that I will share with you today apply across the board into other forms of computational thinking. So my research program has focused on how can we effectively integrate computational practices in the, I guess, engineering undergraduate curriculum. I want to mention that. So when we look at education, we sometimes look at instructors and faculty members. That's the teaching side of things. But we also look at students, and that's the learning side of things. So I will focus more on the learning. I have studied faculty members. I have studied how professors teach computing, how their beliefs about how to teach. But in this case, we are going to focus more on the side of the students and how we can support them better in the learning process. So the way I do research is in the classroom. We identify a problem in the, like a learning need. You can see that arrow there. And once we know what is a potential issue, we design, we deploy our innovation in the classroom, we do this iterative process. So sometimes I will show you just findings from a study, but we do iterate and do multiple studies in the context of a classroom. So you can think of that as an engineering design process. You find a problem, you invent a solution, and you evaluate it in the context of your classroom. And the good thing about this approach is that it can provide solutions immediately to your students, but it can also contribute to new knowledge in engineering education in this case. So I'm going to tell you first, trying to identify the problem. We started, I think it was 2012. A colleague from Johns Hopkins University, he's an engineering professor, and they wanted to integrate computation in the context of the material science program at their university. Now, this is different here in the Czech Republic, but in the US, computer science usually is a separate college, and then the engineering college is a different one, so it's not as well integrated as in other countries. So usually computer science teaches the introduction to programming for all majors, or for science and engineering majors, and then for non-majors. So as you can imagine, the way computer science is taught in an arrangement like that is that it is domain agnostic. So the innovation in this case consisted of taking back that introduction to programming course and teach it in the context of material science and engineering, which was the program. So there was no instructors from computer science, but the students were supposed to learn programming. Can I point with this? No. The angle is no good. So they were supposed to learn programming, and that's the CPMSE is computational material science and engineering. The idea was to learn programming in the context of the discipline, and then we had 6 core required courses that are more science-oriented, but we introduced 2 to 3 computational modules in each of those. So basically a project in the middle of the semester, a project at the end of the semester, maybe one more project. And then the students would learn about computation, modeling, or simulation. At the same time, they were learning about biomaterials, kinetics, thermodynamics, and so on. So what we wanted to learn was, can students learn better the engineering or the science if they learn through computation? So really, computation was the vehicle to learn better in the disciplinary domain. We also wanted to see if their prior programming preparation, including our newly designed course, would have an effect on students' performance. We also were looking at what type of computation software would be more useful for the students, and then if they had positive attitudes toward learning programming. So here is what we've learned, and I'm not going to go in detail over the methods. Let me just focus more on the findings. So first of all, when we talk about approaches to computation, we had sort of like 2 conditions. One condition was, we call it the configuring approach, and this is when students use expert domain-specific software modeling tools like COMSOL, or these are used by practitioners. And then we also had what we call the programming approach, where students used to enter code in MATLAB and so on. So, really the way they interacted was either configuring a graphical user interface, or writing functions, or adapting existing functions, and so on. So again, this is the configuring approach, using graphical user interfaces, and then the programming approach. So we measure students' learning before, so they had the lecture, then we gave them this computation project, and then we evaluated them before and after. So pretest, lecture, it was lecture, pretest, project, and then post-test. So we were measuring what they got from the lecture, which is, and I apologize for the colorblind people, the red bar is basically what they learned from lecture, and the blue bar is what they've learned after doing the computation software. Now, what are these groups? These are students who had no programming background, students who had 1 course, a programming course, students who had 2 programming courses, 3 to 5 programming courses, and our course, disciplinary course in computation, modeling, and simulation. So we were measuring these in the context of the disciplinary courses, this is not the computation course, but the other courses. So as you can see, students were learning more when they use this configuring approach, regardless of their programming background. So there is really no pattern, except this one that was maybe the sample size was too small here. But they still benefited, although not statistically significant. So it seems that it was helping students to learn better the concepts. Now we look at the case of the programming approach, and the story is slightly different. So again, we have the students with 0, 1, 2, 3 to 5 programming courses, and our course. Now, they took the course the previous semester. So it is interesting for us that our disciplinary programming course was having the largest increase, although some students were doing already very good. You know, programming background seemed to have some sort of effect. So there was something intriguing about this result. We also look into how confident and the value they saw in programming. And again, this pattern is, in a way, fascinating. 0 programming background, 1 course, 2 courses, 3 courses. These are the students who took the previous year the CP/MSc course. And then these students were about to take the CP/MSc course. So all of them were increasing their confidence in integrating computation for learning and for doing their disciplinary work. These students, it was their first exposure to programming. Again, this was at the beginning of the semester, and then at the end of the semester, they significantly increased their confidence. So something was working, but something was intriguing, but we wanted to learn more. So what we did next, we needed to change the methods of research. We were doing the traditional pre-test, post-test. We went qualitative. What that means is that we actually wanted to see how students were solving the problems. So we actually conducted a think aloud procedure. We basically recruited students. We brought them to a lab. We asked them to solve the problems in front of us. We were recording their interaction. We were asking them questions, and then this type of work takes many hours because you know, watching 15 minutes of a recorded interview translates into 1.5 hours of analysis. So it took us like 2 years to try to understand what was going on. So we had 12 students. We recruited 12 students who were more doing a configuring problem, and 12 students that had to engage more in the programming. So the first thing we did was to identify what steps they follow. And roughly, these are the procedures they follow. So first, they had to define the model. Then they have to develop the model. Then they have to conduct the experiments and do the analysis. So usually, I guess the heavy programming aspect happened here, right, in the configuring approach, and then in the simulation development, the programming approach, and then the configuring approach. So you can see there are some sort of similarities. Once the model is developed, students can engage in simulation processes. So what do you think were the toughest steps or the hardest steps for the students? Yeah, at the beginning, but I think where they struggled the most was in the middle, for both approaches. Why? If you have ever used Console, it's a very complex software. It has multiple tabs, many things to configure. Unless you are an expert in using the software, it is a steep learning curve. Then in the programming approach, of course, you have to think about partial differential equations. You have to think about syntax of the programming, and also you have to think about the science. So both of them, but since the programming approach was more challenging, we decided to focus more on that. So that little envelope there is what was a key finding. What is the take-home message of this preliminary study? Well, first of all, that the students benefit more on the science when, they don't really have to think a lot about how to create the model. That was our first finding. We also found that in the think alouds, when they had to program the model, actually they have struggles doing mappings between different types of representation. It was hard to abstract the science into a mathematical model and then abstract the mathematical model into the programming or algorithm to solve or to represent a particular type of phenomenon. So we decided to take a closer look into what is happening in the programming, not only because the findings were intriguing, but also because there is zero research published around how students learn programming in the context of engineering problems. So we came up with a research question to continue our investigation. We wanted to see how students think about solving problems, but also how they apply strategies. So those are called cognitive processes, and that's applying prior knowledge to solve problems. And then metacognitive processes are basically strategies to solve problems. So we wanted to see cognitive and metacognitive reasoning, and for that we had to look at the literature of expertise. There, if you look at research on expertise, usually educational psychology focuses on this, on characterizing expertise. And educational psychologists came up with two different approaches to expertise. An absolute approach to expertise, that's you, professors. You are experts in your area, experts in your field. But then there is a relative approach to expertise, meaning what students can accomplish from the beginning till the end of the semester. Basically, have they fulfilled the learning objectives of the course? And one approach to study relative approaches to expertise is adaptive expertise. So this theory explains learning in terms of two dimensions. We have on the x-axis, we have the efficiency dimension, which is basically how quickly you can solve the problem. And then on the y-axis is the innovation dimension, meaning what strategies do you apply to basically solve a problem. So again, this one, you can think of this as the plug and, they just plug the equation. They don't understand what the equation means, but they immediately know which equation they have to use, and then they solve the problem while not really understanding the meaning of that. And then innovation is more like a trial and error approach, really also not very good at thinking. Or sometimes it's fixation, like, they do the same error many times, and they don't step back and think about what is going on. So those are the two dimensions. And then the idea is that you have a novice, and you want them to develop adaptive expertise, which is that corner. However, ideally, you want them to go through that path, right? But sometimes they might take other paths. They may first be more focused on mechanical solutions, and then after a few years, they may finally get it, or they might be lucky and find a solution that executes, and then later on might be able to really understand the solution of a problem they came up by randomness or just because they check the solution. So with this theory in mind, we want students in a way to move through this optimal adaptivity corridor in which you try to be efficient as an instructor. How can you help them go into this more, I guess, linear path of learning and try to avoid other paths that are less efficient? So that's what we try to do. In this case, we focus now on the programming course. We wanted to see how this theory of adaptive expertise looks like. All the students were passing this class, how this was translating into a particular problem-solving space. So again, this is the programming course. Students had 4 projects throughout the entire semester, And what we did, again, we used qualitative methods. We took out students from the class. We asked them to solve problems for us. We recorded the interaction, and then we did the analysis. Now, this figure here, actually, let me just, I'm not going to go over the details. I'm just trying to let you know that we were very thorough in our analysis. We first tried to identify what is cognitive knowledge, and we were trying to coming up with categories based on what students were doing, how students were applying strategies to solve problems, and so on. So it was a thorough analysis, and our theory helped us make meaning of our findings. So I will show you how. So first of all, we identified two main ways in which students apply their prior knowledge. So that's the cognitive dimension. And then there were students that were more focused on the code, and students were more focused on the science. So the implementation-oriented students were making their code execute, but they had troubles making interpretations of the output of their codes. Then we had the students who were connecting the science to the problem using mathematical models, and they use the scientific approaches more effectively. Then on the other dimension of our matrix, we had the metacognitive approaches, which basically there were students, these again are problem-solving strategies. Some of them were jumping into, okay, let me get the coding quickly, right? But others took a step back. They were planning more. They were making connections to the science. So we took our students and we distributed them. These are the 11 students that did the analysis, and some of them had different orientations based on the way they apply their prior knowledge and the way they solve problems. And so once we did this categorization, we were able to bring back our theoretical framework, and in a way, this corner was the action implementation oriented. I think I do have animations for that. So these students were focusing on completing the project. That was their goal. They wanted to be done, they wanted it to work, and we had a pretty good number of students. The L actually means that they were low performing in the course, and the H means that they were high performers in the course. Then we had students who were more focused on invention. They just wanted to come up with something that worked, maybe something creative. We have only one student there, so it was really not very meaningful. These students were focused more on automaticity, and then what we really wanted was the students to be in that quadrant at the top corner, that they were focusing on understanding, meaning that they understood the code, they understood the science, and they were able to make the connection between the code and the science. So just because we have just those two corners had more participants, I'm just going to give you a quick summary. The action implementation-oriented students relied more on context-specific procedural understanding, while the students in the other corner, they were making more connections to their background knowledge. They were checking their code multiple times. They were also generating more goals and strategies to approach their solutions. So what we've learned from this second study is that students, for them to develop this adaptive expertise, they do require to apply both prior knowledge and strategies to approach problems. So they were using the science, they apply skills, they check their code, and then they tested their solutions as they went through the process. So that's the other thing. You've seen that in programming. Sometimes students generate a long code, and then after a while they decide to, oh, maybe I should test my code instead of doing it, in step by step, so something similar. So we come back to our theory, and if the theory says that computational adaptive expertise can be developed. Now, there is this idea of the optimal adaptivity corridor. The question is, can we design instructional supports or instructional materials that will help them? So now we are looking at what can we do, right? We found a problem. We have a sense of why students struggle. The question is, can we help them? And then that's probably the second portion of my talk, is focusing on giving you some strategies of what are the things you can do to help students. So luckily, there is this new technological opportunity. Are you all familiar with computational notebooks? So computational notebooks, these are Jupyter notebooks, Google Collaboratory. They can execute code in a browser, which that is a huge accessibility opportunity, I guess. So just to give you some, this is one of them. We created this notebook. We helped a professor in mechanical engineering redesign all his laboratory assignments. You can use figures. You can add questions to students. You can provide explanations, and then students can execute code. So it really provides a lot of functionality that is helpful in helping students learn. So you can see there that that is the laboratory assignment. Professors actually embed videos of themselves explaining concepts. That is the code. You can execute the code. It generates graphs, and so on. So it provides good technical opportunity for us to innovate. So now we have to think about how can we support students. And a term in education is called scaffolding. So what is scaffolding? Where the term is coming from? Well, you Czechs are experts in scaffolding. Is the idea that that's a scaffold. You provide supports, so the students develop some sort of skill, and then you remove the scaffold, and then the student ideally, happily continues their path toward learning. So it's a method where teachers offer a particular kind of support as the students learn a new concept or skill. So we look at theory of scaffolding, and in general, there are 4 families of supports that you can give students as they learn. So let me just walk you for an example of each of them, and then that's the end of my presentation. So sense-making scaffolding refers to ways to support students so they can understand the real-world phenomenon. That's the definition. And then how to translate between different representations. So the representational competence is important for sense-making. So workout examples is a very common technique. It's a technique in programming, it's a technique in physics, it's a technique in mathematics education. It works. The idea about a workout example is that you basically provide the example, the solution to the example, an explanation of the example, and then the students learn from you by studying the example. So we created workout examples for the students. That's kind of the template for the project. That is the solution. And we provided students with steps. We created nice videos and so on. So we tested them now at Johns Hopkins, but also we were bringing those innovations at Purdue. We were working in a thermodynamics class, and in 2 different contexts, we gave students workout examples. So what did we find? Students couldn't care less. And that is a very common problem, right? We do so many things for the students, and then they don't use them. What should we do? We ask them for points. Well, we had a problem, right? The students were not benefiting from the examples, even though we mentioned the examples are there for you. We were tracking downloads, and nobody was downloading anything. So we needed to look at other type of support, right? So we basically look into articulation. So articulation is a form of explaining. And we wanted the students to create explanations or arguments. What was the idea that we got? Why don't we ask them to comment the code as a form of self-explanation? So we gave them the examples. You have to comment the code to explain your thinking, and then you will have to do that for 6 assignments, and then you are done for the rest of the semester. So again, we were looking into a couple of courses. We asked them to comment the workout examples. We did qualitative analysis. We do hierarchical clustering. We did ANOVA. Anyways, a lot of analytical techniques. So what we found was that students comment code in different ways. Students who were more experienced tended to write shorter comments, more simple comments. That's perfect because they don't need them. But the question is about the students with low programming ability. They were explaining themselves more. They were writing longer comments. So, because they felt they had to explain themselves or understand better what the code was doing. Now, we characterize the types of explanations. Some students provided very little explanation or unrelated explanations, so that was not good. But then a group of students provided limited or mechanistic types of explanations, mimicking probably what the code was doing, not connecting it very well to the science. But what we wanted to see were students who were more principle-based in their explanations or more goal-based, basically the functionality of the code in terms of the science problem, or the representation of phenomena in terms of the code. So really, instead of this variable is the variable A, is this variable represents the atom, so you connect using the comments in the context of the science. So what we've learned, how can we elicit understanding? Workout examples are a great strategy. And explanations of workout examples, so the students providing the explanation, helps them teach themselves the concepts. What would be interesting to see is, can we teach students to do good commenting, right? We talk about arguments, and there is a way to form good arguments. Can we teach them how to use code commenting in a good way? So that could be probably a next step. Let me just move on to the other type of scaffolding. We have process management scaffolding. And one of the things that we notice among my engineering colleagues is that they ask students to generate MATLAB code, and then they say, OK, submit the M file. That means the MATLAB code. And they don't ask students to use the code to solve the problem. So there are many things that happen behind the scenes, if you will. The students, they go home, and we don't know what happened when they learn because they have to work on their projects. Can we guide them so that they make that process more explicit? So very quickly, many times, professors want to see that. The model, the specification, the implementation, but there is an opportunity to ask students to also talk about how they plan for a solution. And that is something that we ask them to do. Then, how can they can use the model to solve the problem? So really, once you do the programming, can you engage with the science? So you actually give them a problem, and then they solve the problem. So this is an example of a programming, a planning stage. The students decided to come up with a flow chart on how they would approach the solution. Sometimes we ask for this planning stage 1 week ahead of the submission stage, so we can give them a quick feedback on their thought process. Some others just used text. Some others use equations. But really, are they thinking through a potential solution rather than running and typing the code, right? So this is the purpose of asking them to make explicit their planning steps. And then the last type of scaffolding is reflection. So reflection is a form of learning. We have been asking students to reflect not just how much they learn or what is difficult to learn, but also what they do when they struggle. Sometimes they get stuck and they don't know how to continue. What are the strategies that they use? So, we have been developing this model in where they engage in the modeling cycle, but at the same time, they engage in self-regulated learning. And again, reflection is a big portion of that. Here are some reflection prompts that we give them. What skills did you have to develop to accomplish the project? What aspects of this project were the most beneficial on your learning? So again, we give them different prompts. So they talk about, in this case, each team member did their individual reflection. Sometimes they reflect together as a team. And my colleague she's teaching a class of thermodynamics with 200 students. And she said that the students really benefit from this reflection process because kind of help the students identify the issues that they have and maybe take steps to address their learning deficiencies. So to conclude, here are a few forms of very quick and easy, in my opinion, ways in which you can support your students, providing them with these scaffolding bits as they engage in computation, modeling, and simulation. If you think about it, to help students in their cognitive approaches, these two strategies are the most helpful, and then those other two help them process their metacognitive approaches. So coming back to the theory, aspects to help in their understanding, and aspects to help them in the problem-solving process. So again, I'm very, very, very close to my end of my presentation. What we've learned? Well, first of all, that computational adaptive expertise can be promoted, so that's a good thing. We can do that by helping students enact all the stages of the modeling process. My colleagues who teach graduate courses, they always tell me, students don't check their code. Because the fact that the code executes doesn't mean that the solution will solve the problem. So they really want to teach validation and verification processes. So what do you do so that they practice those skills? Well, we give students test cases. So there are multiple things that you can do so that they do the planning, the validation, the verification, and so on. We also talk about how to make connections to the disciplinary knowledge, workout examples, and engaging meaningfully with the workout examples, in this case, by having them comment the code. And then, of course, to have them monitor their process. Students themselves, learning, have to be reflective practitioners and thinking about, okay, how am I doing in my learning process? The idea about scaffolding, and that's why it's like in a light color, is that you should remove them. We still haven't tested the removing of the scaffolding. Sometimes the students are first-year students or second-year students. We actually did a study with students who were about to graduate, and they didn't need as much support as the more junior students. So that's the end of my presentation. I do want to say that this work has been supported by National Science Foundation, but very importantly, my colleagues who teach the courses and who allow me to experiment with their students is very important. And they are very open and flexible to try new things. And of course, multiple graduate students who have contributed with their research. So I gave you all the recipe. Everything is in this book. It actually comes with projects and examples, but it's a very quick reading. Probably you can read it in half an hour, but you were hearing this presentation. It's an open access book, and thank you so much for your attention.
Thank you, Alejandra, for your presentation and talk. And now we have time for questions from the audience. So feel free to ask any questions, or you can even share your experience with using novel methods in education. So don't worry, ask questions.
Yes.
Vlastimir, please use the mic.
Yes. Thanks for the talk. I would like to ask you if you can compare somehow numerically the scaffolding approaches. As you said, the first one does not work, giving examples, but is it possible to somehow express, let's say, kind of unbiased efficiency of these scaffolding approaches?
Well, that's a really good question. One of the advantages and disadvantages of using design-based research in the context of a working classroom is that sometimes it's not possible to have a controlled condition, because you want all the students to benefit from the learning opportunity. Sometimes it means that some students won't get, the benefit of that. We do have studies in which we have translated qualitative analysis into levels of understanding, and so we do have that, but I don't have it in this presentation because I wanted to focus on the practical side of things and not on the analytical approaches. But we have been doing continuous studies in the context of multiple classrooms, and we've learned from students' performance. We evaluate their projects. We see how, if there are concerns, for example, in a recent study, we identify that students still struggle with interpreting the output of the simulation, basically the plots, what the plots mean, and then we add more support and we remove them. So instead of giving you a percentage, we have a big picture of how this looks like. We look at learning, we look at confidence, we look at performance, we look at anxiety. So we try to be very thorough, but it's very difficult to tell the whole story in one paper. So we do have multiple ways to measure it, but I cannot tell you it's 90% more efficient or 20% more efficient.
But still, I don't understand why, at least for my generation, learning by example was the major thing to do, or because we studied some books, and then, for example, for some math problem, we tried to solve it, and this was basically many things, examples, and sometimes giving the let's say, help of professors or some book, whatever. But this seems to be connected with the generation that today this, let's say, approach does not work anymore, or because of, I don't know, mobile phones or something. Do you have any, let's say, intuition what's behind that?
So one of the things I mentioned is these things make sense to many people, because we were students, we experienced these things. What it is not out there is the research behind these things. So we know in physics, workout examples, and in mathematics, we know they work. There is no research in programming, just recently. And when it is in programming, it's not in the context of engineering or biology. It's usually in the context of programming middle school children and all that. So one part of the story is to tell the story with the foundation or the evidence from research. And not all research is a number, but more descriptive type of research and more qualitative. Yes, this is a form of hand-holding, because you want to support students. There are other strategies. It's a continuum of support. There is this approach that is called productive failure, that you really want students to struggle and fail, so they learn from failure. And that's an approach. This one is supporting them along the way. And productive failure is good when the students have a good foundation, like students in the 4th year of their bachelor's. They can go through the productive failure because they know more of the physics, they know more of the programming, they know more of the But first-year students, they are just coming out of high school. They come with different programming backgrounds, and we feel that this approach of supporting is better for this type of students. And yes, there might be students might change because of generations. And I was talking the other day, I cannot lecture for more than 15 minutes because everybody, will be on their phones or, but yeah.
Thank you.
Let's try it. It works.
Hi, thank you for the talk. I have a question regarding one of the first slides that you showed us. You were talking about the configuration approach and programming approach, right?
Yes.
I understand the configuration approach. So there's some specialized software for the particular problem that the students were solving, and they somehow input some parameters and run a solver or something, get some plots out of it, and they use that. But what about the programming approach? Is it that they program the whole task from scratch, or do they also have, let's say, equivalent higher level tools that they can also use, but just use them via code,
Yes.
not graphical input?
That is a great example, and there were different levels of variation of how much students had to engage with the code. Sometimes, well, first of all, in engineering, it's very unlikely that the students will start from a blank screen and start typing code. That's more common in computer science, for example. In engineering, sometimes the skill that we want is that they download some code and then they are able to adapt it for their own problems. In this case, there were multiple levels of engagement in that regard. Students had to program a function, or we gave them a template, and then they had to kind of fill in the blanks with code. So we didn't really track those forms of engagement with the code. That was more later on into giving them templates versus giving them a simple example where they had to extend versus giving them an incomplete example. So those are different ways in which you can engage students with programming. But in this particular case, they had to add a function, or they had to change, add more variables, program one more thing. So it was not just execute, right? They had to do some programming or engage with the code somehow.
Okay, understood. Thank you.
Thank you. Thank you for the question.
Any other questions? Okay,
I have the mic, so well, I have a question. I understand that actually the scaffolding approach can be very useful for like freshman students of the bachelor studies, for example. Do you think there is a danger that providing too much support for, say, master students could actually hurt, that they would have too easy studies, or they would be like too much guided, like kids, and they wouldn't like it actually? Do you think this can happen?
Yes. So I guess there are different types of modeling and simulation skills. I understand that the easy things, students don't need that kind of support, or master students, maybe you want them to struggle more because that's what it's easier. But when you have a class of 200 students and you want to support all of them, that's a different story than when you have a class of 7 students and you give them the space for them to struggle. So, but still, there are some quantification processes. I think that's a very complex modeling and simulation skill that, these are very advanced topics. And by the way, in the book, we have a learning progression of modeling and simulation of what are things that undergraduate students can do, like generating simple models and things like that. What are skills that more at the master's or PhD level? So we did that through asking experts in the field on what are the modeling and simulation skills needed for the future professionals in engineering. So So I guess the answer is yes and no. Like maybe if you have a quite large class, you maybe want to accommodate. So that is the other thing. You have to think about what is feasible, right? Like Johns Hopkins is a small university. They had 30 students in a class. Purdue University, we have 200 students. So there is some sort of adaptation from one context to another. But still, the idea of workout examples was useful for both, even though, you know, we provided more in one institution or less in another institution. So the same by grade level. And actually, Johns Hopkins students, these are very, you know, their admission process is more rigorous than Purdue, and so, you know, those students might be better prepared, stronger mathematical foundations, and so on. So, yeah.
Thank you.
I have one provocative question, because that's me. At the very beginning, he showed us the guy who is the photo, the guy who is very unhappy sitting in front of a screen, having some difficult source code there and overloaded. And then the dream is to have a happy female student on the next slide. So my provocative question is, how many students have you turned from unhappy to happy using techniques you just described?
Yes, so over and over, we keep surveying students at the beginning and at the end of the semester, looking at their levels of anxiety, looking at their confidence, looking at their interest, looking at their enjoyment. They all increase on average, but significantly, the confidence in themselves engaging with programming, that is the consistent metric that has a statistically significant increase from the beginning till the end of the semester. So confidence is something that we have measured over time.
Great, and one more, not so provocative, but when you showed us the graphs, the result of those two approaches, one is tuning parameters and the second is programming.
Right.
And there I saw the increase of better results between the pre and post tests, but none of the results was excellent, perfect. So all the graphs stopped at, let's say, 60%, and no student achieved 100%. So
correct.
Can you either comment or explain that? Or perhaps you could show the graph I'm trying to remind of.
So that's a really
very sorry,
point.
very beginning. I guess that was slide number 5 or 6.
Yeah, I could probably just go back.
Okay, I can press it instead of you, and you can talk.
So the idea behind that was we created these tests for research. So one thing is the grade that they get in the class, and another one is the questions that we ask for the purposes of, like this one, for example.
For instance, here, I see on the left there's a high achievement. So there is no high achievement. So
yeah.
What's
So
wrong?
this is this is. Sometimes you teach your class, you have your exams, your tests, your quizzes, and then all the education researchers come and add more stuff. So this is adding extra stuff that was not part of the final grade of the class. But I do have to say that I guess engineering is a difficult major. I don't think it's very uncommon to have students who do everything perfectly, even though they are smart students. It's just a scale we can.
So this high achievement is really high.
Yeah, like having all the answers 100% correct.
Yeah, of course. It depends on the point of view. Okay. So now I agree. Thank you.
But
Thank you.
You are right. There is still room for improvement. So how can we use the project so that we can help them reach that? I guess Peter Felker has this experience. Sometimes the alignment between the test and the intervention also takes some time to have it right. Sometimes we ask questions that we're not practicing the module and things like that. So anyways, that could be also the result of students not being guided in every single question of the test as part of the project. So, okay. Yeah.
Thanks.
Yes.
Okay. Excuse me, I'd like to give you mic.
Okay, if I look at the second two piles, it looks like they are lower than the first one. So after one course, the results are worse. Or am I wrong?
No, this is how many programming courses they had in the past. So this is the same.
Yes.
Students.
So after one course. The blue pile is...
Yeah, we don't know what happened.
So it would be good to skip the first course? Or?
Maybe. Yeah. And again, I don't
have the numbers. This is nice observation, and it shows how our teachers are perfect on watching your slides and finding some theoretically mistakes or issues. Issue is much better word, sorry. Okay, so the last question before the break.
Thank you. How much preparation effort does it take approximately to come up with this scaffolding approach in a single course? I saw there were, I think, 10 people in your lab, all of them evaluating or just working on the approach. So could you
yes.
quantify?
Yeah, so I do want to say that one of them is about to get tenure at so it's not like all of them at the same time, but over the span of 15 years, I have collaborated with a few faculty members and the students who have done their dissertation work around that. But it actually, the preparation is about the same time you have to add to your teaching. Now, in my relationship with my collaborators, they find it beneficial because I help them, for example, generate evaluation rubrics. So basically, they design the project, they still have to give a project, and then we meet and we decide what are the difficult points for the students, what kind of support can we provide. So maybe 20% more work in terms of, because you still have to design projects for your students, but then meeting with me, deciding what to do, and then we also, again, generate ways in which we can evaluate the projects. We help the professors with that. So many professors use let me take points out. Our way is like, okay, what is the skill that you want to evaluate? What is the level of performance? Below basic, and these are the characteristics. Proficient or basic, these are the description of a basic. Proficient and advanced. So then we can quantify where they are doing poorly across the board, because we have the rubric that is, there is no, yeah. So usually a rubric has the levels of performance. So this is 1 point, 2 points, 3 points, 0 points. And then you have skill 1, skill 2. And then you can see that 70% of the students are at the advanced level, while 30%, so you don't have to worry about this skill. But sometimes you have 50% of your students performing at the below basic, and the other 50%, probably they are here, or maybe the percentage. But then you know that they have an issue, and that's how we track students' overall performance. We can identify skills. We teach the TAs how to do this. We also do it, and then we cross-validate our scoring against the professor scoring. So is this idea of the rubric is clear?
I think it is, but I'm not sure if we meet in the question. I was wondering how much effort for you or your collaborators it took to transition from, let's say, a conventional approach to teaching to this scaffolding?
Yeah, so that's a good point. I recently started a collaboration with my colleague in mechanical engineering, and he was doing traditional laboratories. So actually, we took his laboratories, and my graduate students transformed those into notebooks. So we help the professor, because we know that they are busy with their mechanical engineering research. But guess what? Now he's going to offer his course online, and Purdue Online is going to pay him money because everything is online. And we have the experiments as notebooks and so on. So it takes a little bit of effort, but we are very conscious about faculty time. We don't want to overwhelm faculty, otherwise they don't want to work with us. So we try to help as much as possible. And it's also a professional development for my own graduate students, because they have to learn how to design good learning materials and so on. And sometimes we do take care of the grading. So the professor downloads all the projects for us to score by rubrics.
Well, since it's my duty to care about proper timing and schedule for this afternoon, let me stop the discussion. Not to stop, but to break the discussion right now and to inform you about the following. We have about 25 minutes for a break and for refreshment, which is prepared for you. So feel free to combine refreshment and or even further discussion with Alejandra. And then we will start at 2:30 with the second lecture given by Bedřich Beneš. So let's thanks again Alejandra for the talk and discussion. Thank you.
Thank you.
And I also thank you for your questions and the discussion, and we have 25 minutes break.